start the second day of our workshop. It is a true pleasure to have with us Alexandre Belin from Iran. He will tell us all about Fortuity, and in particular in ABJM theory. You have 1 hour.
Great.
Okay.
Thanks a lot. Thanks for the invitation. It's really great to be here. Unfortunately, I'll have a very short stay, but still, I think I've been to Trieste 3 or 4 times, always in the winter. I hear one of the great highlights of this workshop is the swimming components, which I've never experienced. So I'm very eager to see how that goes in a little bit. Great. So what I'll tell you about today is something that I'm really excited about right now. So the talk will primarily be based on a paper that we wrote a few months ago with great people in Milan, Alberto, that I'm sure all of you know, but also Palash Singh, who's a great postdoc with us, and I really want to highlight the contribution of Rita Vadela. This is pretty hardcore stuff that I'll tell you about. I'll try to tone out the details. She's a master's student, and she really did a lot of this. She's amazing. She's going now to Daisy for a PhD, and will start in a few months. And there's going to be a little, small piece of work in progress. I'll try to update you on what we discovered at the end of the first paper and what we're trying to understand now. So before telling you exactly what Fortuity is, I want to just try to give you some motivation. What are the types of questions that we're trying to understand here? So maybe the first question is, what is the difference between a black hole microstate? I'm going to take that to mean something which, through ADS-CFT, black hole microstate, which something through ADS-CFT is dual to a geometry with a horizon. And a back-reacted gas of gravitons, which is a geometry without a horizon. What is the difference? Then can we ever make this difference sharp? Well, that's one of the things that we would like to understand. The second question is, what is a black hole at finite G Newton? Okay, in the language of ADS-CFT, this is finite n. So the thing that we understand well is semi-classical gravity. That's a limit where we take G Newton to 0. Okay, and through ADS-CFT, this means that LADS to the appropriate power over G Newton, which we usually call n, or n squared, and n equals to 4 super Young mills, goes to infinity. This is the semi-classical large n limit that we're all familiar with in large n gauge theories, which in ADS-CFT gives us semi-classical gravity in the bulk. We take this limit all the time, and there we think we can trust geometry. We can understand what a black hole is. But perhaps we can be even more optimistic or more ambitious and try to understand what is a black hole at finite G Newton when we're in the sort of deep quantum gravity regime. Can we understand what that is? Does this make sense? Okay. So this is maybe part of the second question, and another part of the question is, here what we're doing this, when we're taking this limit, we're really not in a fixed theory, but we're rather in a sequence of theories. We imagine we have n equals to 4 super Young mills with gauge group SUN, and when we're taking this limit, we're really scanning through theories, looking at different values of n. So we're taking a limit in theory space when we do the semi-classical limit in gravity, and what can we, another part of this question is, what can we understand about this limit? What does it mean to vary through theories, and is the n dependence of black hole physics smooth or not? Okay, so these are sort of two of the motivation questions for thinking about what I'll explain to you in a second, which is Fortuity. And today, I'm going to focus on supersymmetric black holes. And as we'll see then, we can make some of these, we can answer some of these questions in a sharp way. It's a very interesting endeavor to try to understand how to generalize the lessons that I'll tell you about today to the non-supersymmetric case, although there's been very, very little work that actually did that. Now, for supersymmetric black holes, I guess we have one of the one of the famous authors of, as we've known from '96, Kumaran will be giving a talk today, he's interested. We just saw him in the coffee room. As we learned in the late '90s, there's been a lot of success in string theory and then later in ADS-CFT in matching a superconformal index which counts the microstates of the microscopic theory to the entropy of a black hole. So this is the degeneracy that counts the number of microstates, maybe with -1 to the f inserted. And we've understand very well since the 90s how to match this to e to the s Bekenstein-Hawking formula of the black hole. Okay, so this is, the work of Strominger and Baffa in the 90s, plus many, many developments after this. And more recently, in ADS-CFT, the work of Francesco, which I did not see, and Alberto and Cyril, but and also later developments in all kinds of contexts in ADS-CFT. So this we understand well, and this is great. I mean, it tells us that we can do a microscopic counting of what the Bekenstein-Hawking formula is telling us. This is really fascinating, but perhaps we can, so a third goal that we would like to understand in this program is, can we do better than this? Can we do better than a count? Can we do better than a count? It's already amazing that we can do this count, but can we, perhaps it's time to be ambitious and ask, can we do better than just the counts? Can we understand the actual structure of the microstates? So these three questions are essentially what motivated the start of this Fortuity program. Okay? These are the types of questions that we would like to understand. And so what is Fortuity? I think now it's time for me to tell you what that is. So in a very nice paper by Chang and Lin, they proposed at least some partial answers to these questions. And they proposed to study the Q cohomology of the gauge theory at finite n. Okay, so you pick some supercharged Q, and then you define the Hamiltonian to be the anti-commutator of Q and Q dagger, and then you study the Q cohomology of the supercharged Q, meaning you try to find local operators in the CFT, such that Q, when acting on the operator, is 0, but O is not. So Q is nilpotent, so obviously if you find some operator O prime such that when you act on it with Q, if you act with Q on the second time on this, you will obviously get 0, so you're trying to find all the operators that are Q close but not Q exact. Okay? And that's the cohomology of the supercharged Q. So they said, let's study this problem in the large N gauge theories. And then there can be two different types of operators that you can find that satisfy this property. There's what are called the monotones. So the monotones are operators such that when you act with your operator O on it with a supercharged Q, you find 0, and that is true for all values of the rank of the gauge group N. Okay? And these you should think about, so the proposition is that these are dual to gravitons. Okay? So you might think that all states, all members of the cohomology have this property, but it turns out that they're not all like this. And there's other operators that have the very weird feature. So these are what are called the fortuitous operators. And they're such that when you act on Q with O, what you get on the right-hand side is something which is a trace relation So, you know, all these operators in the standard case of n equals to 4 super Yang-Mills, all the operators are transformed in the adjoint of the gauge group. So you need to, all the letters in the Lagrangian, or all the fields in the Lagrangian, so you need to assemble them into gauge invariant operators by taking traces. And it can happen that when you act on O with Q, what you find is a trace relation that is valid for all n smaller or equal than n star. Okay? For example, it can happen that what you find on the right-hand side here is something that is 0 by a trace relation at n equals to 2, but non-zero at n equals to 3. What does that mean? It means this operator is BPS at n equals to 2, but not BPS at n equals to 3. Okay? And if you can find such an operator, then they call this operator fortuitous, and the proposal is that these are dual to black holes. And now this distinction you can work on at any value of n. I mean, of course, this statement is a statement that holds as you scan through the different values of n. But you can study this problem at n equals to 2, 3, 4. You don't need to be in the large n limit anymore. Yes?
There's no case that that could hold for a window of n's. Let's say that they become like that for a window and then they get out of that.
Somewhere in the middle?
Yeah.
No, this doesn't happen because of the nature of trace relations. So trace relations, there's an embedding of the trace relations that become weaker and weaker and weaker as you make n larger and larger and larger. So it's impossible to have something that becomes BPS in the middle and then disappears, at least not through a mechanism like this. It would be very interesting if there's another mechanism that hasn't been found where that would happen.
Sorry, are
yes.
you talking about local operators?
I'm talking about local operators.
Okay.
Yeah. So I'm imagining, you know, putting the, let's say we have n equals to 4 super Yang-Mills. The spectrum of local operators is equivalent to the Hilbert space on the sphere, and the three-dimensional sphere, and that's the standard story. Yeah, would be very interesting to understand if there's a generalization of this story to non-local operators, but as far as I know, that has not been looked at yet.
I mean, I think there are examples in toy models like SYK where if n is too small, then O itself vanishes. And so in that sense, in some sense, there is a window where O is supersymmetric and non-zero. So that could also happen. So O is a trace relation for very small n, so it just vanishes. Into intermediate n, it's supersymmetric, and for large enough
Oh,
n,
you
it's
mean
just non-supersymmetric.
O is a trivial operator at
Yes.
small n, and then it only exists at sufficiently large n, and then if you make n even larger, yeah, that's okay. Maybe that's an interesting answer to the question. I was imagining the question was, can you find some non-trivial operator at all values of n that is always non-trivial but happens to be BPS in some window in the middle? But maybe that's a hint of how you would try to engineer something related to that. Yeah, thanks. That's a nice comment. So let me just try to draw a graph of how you should think about this. So imagine we pick some local operator O that is of this type, and we look at its scaling dimension as a function, or maybe, you know, this is like scaling dimension minus charge or something that measures whether the operator is BPS or not, as a function of the rank of the gauge group. And, you know, we have like n equals 1, 2, 3, 4, 5. So what does this thing mean? It means that the operator for small values of n lies exactly at delta equals to q, it's BPS. But then as you go beyond, let's say in this case n star is 3, then the operator would start to acquire anomalous dimension as you turn on the coupling and would be lifted like this. Okay, and for all higher values of n, the operator would be non-BPS. Okay, this is the idea. Whereas, so this is a fortuitous operator, and I don't think I have color, but a monotone operator would be just one that is 0 all the way for all values of n. Okay, that's the distinction.
So maybe you're going to explain this, but is it why black holes are fortuitous and gravitons are?
So this is the proposal. What is the motivation for this proposal, or at least I don't know if it was the original motivation, but it's certainly how I like to think about it, is that things like gases of gravitons are very smooth in the microscopic sense. You can backreact gravitons and do that at all values of n, and this is smoothness. This is this is why things don't change erratically as you vary n. The fact that this happens, I think, goes hand in hand with the fact that we think that black holes are chaotic. Usually what we mean by chaotic is not what happens to them as you vary n. But you might think that if black holes are representing chaotic objects, it means also their n dependence is very erratic. And this would be a realization of this, is that, it's not at all that these things are smooth as you take n large. Is that, their BPS-ness is not a smooth function of n.
But can one cook up some kind of a partition function which undergoes a phase transition? Can one make it a more rigorous statement like that?
Yes, this is
This
the
contribution to partition function has a jump and that one doesn't.
Well, yes, you can do all of this, and usually things are a little bit more subtle than this, because the point is that something like the superconformal index that I wrote counts everything, right? Now, but there's a question is what dominates that sum, and then you can have phase transition between, we're all, even in the non-supersymmetric case, we're all familiar to this. We call this Hawking page or confinement deconfinement, right? At low temperatures you have thermal ADS or maybe small quantum excitations, and then at large temperatures you have the black hole that dominates. And then you have all kinds of generalizations. It's a very rich structure, actually. In the case of, say, n equals to 4 super Yang-Mills, there's all kinds of interesting transitions that happen. Well, I'm not going to say they're blind to this, they're related to this, but one should remember that the partition function always counts all of them together. So what you're supposed to do if you want to, and I'll explain this a little bit, if you really want to focus on finding these operators, you're supposed to somehow find a way to subtract these operators out. And this is actually very difficult. This is the part that is very hard. We don't know how to do that in full generality.
Sorry.
Yes.
I have a very basic
Yes,
question.
please. Those are
I
the
can
hard
understand
things.
the meaning of the fortuitous. You mean that you apply the Q operator over some operator, and this is not vanished unless the trace relations are
Holds.
Yes.
So here's the
It's a zero only by the trace relation.
Only by the trace relation. So
Okay.
imagine, you have the field in n equals to 4 super Mills, the field in the Lagrangian, there's like the, 6 scalars which you can assemble in complex scalars, x, y, and z. And you build some operator of the type trace, x, y, z, x, y, some operator like this, right? Then you act on it with q, you'll get a different operator, maybe a linear combination of operators. And maybe that thing that you find looks like trace of xyz, trace of xyz, minus trace of xyz, xyz. In general, that at large n, those are just two different operators, they don't cancel. But maybe at n equals to 3 or 2, there's a relation that tells you that trace of xyz, xyz equals to trace of xyz times trace of xyz. Then if that happens, the right-hand side becomes a trivial operator by the trace relation.
Okay.
So this is how you should think about this. And I'll try to, it's actually quite hard to do this in n equals to 4 super Yang-Mills, and one of the nice things about ABJM is that you can write down very simple operators where this thing happens, and I'll try to be explicit about this.
Okay. Are you going to also give a meaning to n star on the gravitation stuff?
No, yeah, so n star is, that's a great question. N star is not something that we really understand on the gravitational side, I would say. The gravitational side, the black hole geometry makes sense in the limit n goes to infinity. And it's very hard from the gravity side to say, well, for a thing of a particular charge, n star for this operator will be this integer. That's a very difficult question. In fact, I think probably what's true is that if you look at all you fix the value of n, let's say it's 1 billion, okay? And you look at all the operators that are fortuitous for n equals 1 billion, you write them down and you ask, what is n star for each of those operators? So the idea is all of them will eventually become non-BPS, but there could be many different values of n star as you tune up. So I don't think n star is it's an extremely difficult thing to capture from the bulk side. Maybe a different way to say something about that question is like, how do you even know from the bulk side that n is quantized at all? That's maybe one of the big open problems in holography and quantum gravity in general. We might think that there's a deep lesson that the cosmological constant is quantized always, but it's extremely hard to prove that thing has to do with non-perturbative physics, and I don't think we really know how to tackle that question at R. And this N star is probably yet even kind of a harder version of that, where now you want to pick out individual microstates and ask for each of them what is the right value of N star. But it's a very interesting question, but unfortunately I think we have very little tools to attack it currently. Okay, good. So this is the story, and so let me just tell you a little bit what has been done or what was done prior to our paper. So fortuity has been studied where? So we can, go up in dimensions and look at all the canonical examples of ADS-CFT. So where this program really started is in n equals to 4 super Yang-Mills. That's d equals to 4. So this is where the most progress has been done and the most states have been constructed. The most operators of this type have been constructed. There's a ton of progress for n equals to 2. You go to n equals to 3, it becomes extremely difficult. And I think for n equals to 4 and beyond, almost nothing is known. So this is, implementing this in practice is actually extremely difficult. But where the most progress has been achieved, I would say, is here. Perhaps that's not quite true. Perhaps where the most progress has been achieved is in the simplest case, which is d equals to 1, which is quantum mechanics, because that's much easier. So there's a supersymmetric version of the SYK model where you can study these questions, and this has also been done, and maybe this is actually the easiest case because you're not in quantum field theory. But quite a lot has been done there. Then in d equals to 2, we have the d1, d5 CFT, which is the canonical example of ADS3 CFT2. This problem has also been studied here. And prior to our work, where you have the other two theories, ABJM and the 2,0 CFT in 6 dimensions, this had not been done. Okay? And this has still not been done. This is actually very difficult. This is a non-Lagrangian. This is also, I think, a very interesting open problem. This is a non-Lagrangian theory. And all the tools that I'll tell you about here are for Lagrangian theories, where you build letters out of the fields in the Lagrangian. I don't even know how to set up the problem here. But I think it's an extremely interesting endeavor to try to understand how to do that. And what I'll tell you about today is sort of fill in one arrow of this gap and look at ABJM. Yes?
So d equals 1 is easy not only because it's d equals 1, but because it says YK, right? If you do BFSS, I guess it's still hard because you have multiple matrices that are not complete.
Oh yeah, that's a
The most important reason is the degrees of freedom of choice YK.
Yeah. So maybe I should have said it's quantum mechanics in a finite dimensional Hilbert space, which makes things. Yeah, actually, I don't know. Maybe you've thought about this, but trying to study this problem in BFSS, I think is an excellent thing to do. As far as I know, there hasn't been much result so far, but it would be a very interesting thing to do. Yes.
Yeah. So what is the D1, D5 CFT?
D1, D5 CFT is, it's well, maybe we don't understand it quite as well as the other ones, but it's you take a T4, a K3, the nonlinear sigma model. One point on so this has a complicated moduli space, this theory, but one point on the moduli space is the symmetric orbifold, symmetric product orbifold of K3 or T4, and then you turn on a gauge coupling that couples the different copies, and this is the CFT dual to supergravity on ADS3 cross S3. That's one of the, it's the realization of ADS3 CFT2 that we understand the best. And it's the low energy. I mean, this is actually very related to Strominger and Buffa. It's the CFT that appears as the low energy limit on a stack of D1 and D5 branes that intersect in the right way. Okay, so let me tell you. I mean, of course, filling in this chart is nice, but it would be nicer if we understand something a bit deeper about it. So what's interesting about ABJM? And there's a couple of features here that are absent everywhere else. Well, let's exclude d equals to 6 for now. So here's the important differences, or the features that make this story interesting. One, there's no continuous coupling. ABJM is a Chern-Simons matter theory where the level of the Chern-Simons terms are quantized, right? This means that there's no continuous gauge coupling, and things like the superconformal index do not need to not depend on the gauge coupling. In fact, we know that the partition function, the supersymmetric superconformal index of ABJM depends explicitly on the coupling. So there's no continuous coupling. Okay, this means that Z depends on K. And that's very different from what happens in n equals to 4 superangles or in the D1, D5 case. 2, there are 2 holographic limits, not 1. Depending on how you scale n and k, if you take n to infinity with k fixed, you land in an M-theory limit, where the theory actually is much closer to this thing than to n equals to 4 superangles. So there's an M-theory limit where you fix k and send n to infinity, but there's also a type 2a limit where you fix n over k and send both n and k to infinity together. And then n over k is the Toph coupling, and then it's very similar to the Toph coupling. Fundamentally, it's still a discrete parameter, but it becomes kind of quasi-continuous in this limit and starts resembling a lot more of what we have here with a string dual. And that's supergravity on ADS 4 cross CP3. And maybe most interesting, including an M-theory one. And finally, and I think this is perhaps the most interesting of all the points, is that in ABJM, not all local operators correspond to just taking the fields in the Lagrangian, making gauge invariant operators, and having that. That does not span the entire space of local operators, and because there are non-perturbative objects, which we call monopoles, and some of the local operators of ABJM are built out of these monopoles. These are a different recipe to make gauge invariant operators in 3 dimensions that you don't have in n equals to 4. Okay? And the superconformal index counts these. This is why there is k dependence in the partition function in some sense. So the superconformal index counts these, and you need to take them into account and understand how to fit this non-perturbative physics into the story that I was telling you about before. Yes?
Can I, very stupid question, why do you call them non-perturbative? I would consider them disorder operators, but non-perturbative in what sense?
They're non-perturbative in the sense that if you do large K perturbation theory, these are not operators that you would see in large K perturbation theory. Okay. They're really things that exist at finite K that you don't see. I mean, they would probably appear as instantons in the 1 over K perturbation theory, but not as perturbative objects. I mean, there's different ways to think about them, and actually probably many people in this room know a lot more about this than I do. This is all the stuff that I had to learn for this project. You know, they correspond to, one way to think about them is by turning on a background gauge field, and this is not, I would say they're not perturbatively related to, to the other operators at large K.
Do they correspond to some classical solutions of the theory, or
you're asking, do they correspond?
Do they correspond?
Yes, I would say yes.
I mean, typically, for, I don't know, in say, n equals 4, I can still perturbatively compute stuff in the presence of an Hooft line or something, right?
Yeah, so, well, okay, yeah. You can do perturbation theory on top of various things that you include.
I see.
But the object itself is not sort of visible. I think it's really like an instanton, right? Like, you can use a lot of techniques from the Lagrangian to do things with instanton, but the instanton itself is not something that you understand very well from perturbative quantum field theory.
It has some non-trivial topology.
Yeah, exactly. I think it's in the same sense. I think it's in that vein.
Okay, thanks.
Yeah, thanks. These are great questions. Okay, so how much time did I use already? Like probably already half an hour?
Half an hour.
Yeah, okay. That's fine. I probably won't get to tell you everything that I wanted, but I don't have a particular agenda. I think I'll just try to tell you what I can in the time that I have, and we'll see how it goes. So this is sort of the motivation, and now we need to sort of dive in a little bit and tell you actually how to build these things in ABJM. And I probably won't go through all of the details. I'll sort of just list the ingredients that we need and then tell you what the results are. And I want to come to something that's more related to the work in progress, which is about sort of an enigma of entropy for ABJM that we don't understand, but that maybe we can discuss and see what to say about them. Any questions before I dive in? Okay, so here's what you need to know about ABJM. So ABJM is a gauge theory. It's different than n equals to 4 Super-Yang-Mills, which has adjoint matter. Here it has matter that there's two Chern-Simons gauge fields, and the matter that you have transforms in the bifundamental of the gauge fields. So it's more like a quiver theory with two UN nodes. Okay, and then you have various types of fields that transform in the bifundamental of these gauge fields, and so you have bosonic fields A1, 2, where the 1 and 2 is some kind of like flavor index, and then you have fermions that I'm going to call psi b that transform in this way, and then you have psi 1, 2a, things that transform. So this is like fundamental, anti-fundamental. This is like anti-fundamental, fundamental, and the bosons I'm going to call them B. Okay. So at general K, the theory has n equals to 6, Susie. But there's an enhancement, a famous enhancement at K equals 1 and 2, where the theory has n equals to 8, Susie. Good, so what is the idea? You pick a supercharge. It's not super important the one that you pick, and in some conventions I'm going to pick one that's called Q34 in the sort of canonical choice of the conventions for the supercharge. And our Hamiltonian is basically going to be, dilatation operator minus spin plus Q3, and I hope I didn't make a sign mistake. So this is the scaling dimension, this is the spin of the local operator, and this is the quantum number of one of the cartons of the R symmetry group. Okay? And so we're looking for things that have H equals to 0, and this is Q dagger, and then we want to study the cohomology of Q. So how do you do that? Well, you look how this Q acts on the various letters of the Lagrangian, and you can see that Q kills A and B. These are actually chiral primaries. They're half BPS operators, and they're killed by the Qs. And it acts non-trivially on the psi's because of the superpotential. So this is how, and this is what makes the cohomology problem interesting. Okay, and there's a similar expression for psi b. And there's also an expression, so these are the letters in the Lagrangian, but then you can also use derivatives, just like we do to build, for example, the descendant operators. The descendant operators under the superconformal group. So there's one derivative that you can have. I'm going to call it D, which is D++. Again, in the sort of canonical. And there's a complicated expression that tells you how you act on Q when D acts on any one of these fields. Okay, and it's complicated enough that I don't want to write it down, but there's some non-trivial expression for Q. So then the strategy is kind of clear. You need to use the AIs, the BIs, the psi-i's, A and B, and this derivative operator, and take into account how the supercharge act, make all possible gauge invariants that are Q closed but not Q exacts. That's the strategy. And in principle, you put this on a computer, test all the possibilities, and figure out what are all the operators and which ones are monotones and which ones are fortuitous. Okay, that's the strategy. So for example, one thing that you can do, so A transforms in the fundamental anti-fundamental, B transforms in the fundamental here and anti-fundamental here. So for example, if you make some operator which is AIBJ, these are the flavor indices, so there's 2 of each. Sorry, I didn't say, but I and J, I wrote it here, right? It goes 1 and 2. So there's 4 operators of this type. This thing itself transforms now in the adjoint of this gauge group. And so now if you take a trace over it, this makes a gauge invariant operator. Okay, and these are the lowest scaling dimension operators that contribute to the superconformal index, and there's 4 of them. Okay? Now I want to keep the discussion about monopoles very short in the view of time, but the point is that at small k you can also turn on monopole operators. And then monopole operators give you new ways, basically they carry some gauge charge themselves, so they give you new ways to build gauge invariant operators. And for example, at k equals to 2, the operator has sort of gauge charge 2, and now you can make a new type of operator, which is, so I'm not sure exactly how to write it, maybe I'll put an m here, and a squared. So a squared was some weird operator that didn't transform nicely without the monopoles, because you could combine a and b's to make a joint, but you can never combine an a with an a. But the point is that in the presence of the monopole, now you can find a way to dress two factors of a with the monopole to make a gauge invariant operator. So
monopole operators are not gauge invariant by themselves.
no, they're not gauge invariant by themselves, correct.
I see.
But you can use them and combine them with the standard letters of the Lagrangian in new ways to make gauge invariant operators. And so this also has dimension 1, but you see that now there's new operators that exist. And in fact, once you add the monopoles at k equals to 2, you go from, instead of having 4 operators like this, you have now 10 of them. Because there's all the ways that you can do this with a's and also with the b's, and this enhances it. At k equals to 1, it's even more extreme, where you can have an operator which is traced just ma on its own becomes gauge invariant. And that means that there's a new gauge invariant operator at scaling dimension 1/2, which did not exist for all the higher versions of k. Okay? So that's what you need to know about monopole operators in this talk, is that they give you new ways to make gauge invariant operators.
But only for small k.
No, so they always give you new ways, but the order at which you get new ways depends on k. So the gauge charge of the monopole depends on k. It's like k over 2. So you know, if you always get new operators that appear at scaling dimension k over 2. This is why you have one at 1. So this is delta equals 1. This is delta equals 1/2. You see that in both cases, these are, I wrote down the lowest things that appear. They always appear at k over 2. So even if k is 20, well, that means that, you know, in the superconformal index, you will see no k dependence up to delta equals to 10, but at delta equals 10, you will get operators of this type, and they will always be of the form trace m, a. Those are always the lowest ones that appear. And then you can do it with fermions and derivatives, and the story becomes much more complicated, but this is sort of what you need to know for today. Good, and then maybe 2 more things. One thing is the superconformal index. Okay, so you can compute I, which is trace minus 1 to the f inserted, x, which is some fugacity that you turn on, which you take delta, which is the scaling dimension, plus the spin. There's all kinds of other ways to refine it with other quantum numbers that measure their R symmetry. This is the least refined superconformal index that you can write down, which will be enough for what we're going to do today. And there's a very complicated expression that you can get either from localization or from deforming the theory on some direction where the superconformal index does not change, and you can then use free fields to calculate it. And I'm going to spare you that expression. It's very lengthy, okay? But there is a closed form expression for the superconformal index that you can use and compute. Okay, you can either go to large N and do all kinds of saddle point analysis, or you can just at small n at small powers of x just extract the first few Fourier coefficients of that superconformal index. Good. And the last ingredient, which is very important, are trace relations. I won't go higher than n equals to 2 today, so it'll be very, you know, basic in terms of rank of the gauge group. So what you need to know just an extremely simple matrix identity that, you know, we all learned probably once upon a time in kindergarten for 2x2 matrices, which is just the fact that any 2x2 matrix M you can rewrite in the following way. Trace squared of M minus trace of M squared times the identity. Okay, this is just an identity for 2x2 matrices that are always true. And why is that useful? It's useful because if you replace M by M1 plus M2, okay, then when you look at M squared, you have M1 squared plus M2 squared plus M1, M2 plus M2, M1. If you want the anti-commutator of M1 and M2. Which means that, and then for M1 squared, you can use this identity for M1, and for M2 squared, you can use this identity for M2, which means every single time you will find this anti-commutator of the two matrices, M1, M2 plus M2, M1, you can replace it by everything else. Okay? And this is just a matrix identity, so you can do this with fields in the Lagrangian always. Okay? And this is the only thing that we're going to need to use. So I'm going to write down some expression that's slightly more complicated, but it's really just utilizing this. We have it here, that's good. Okay, so the one that will actually use it in this talk is the following. So now, of course, these are field in the Lagrangian, but I'm just viewing them as 2 by 2 matrices where this identity applies. A, M, B, N. Now this has 6 of them, and I assume that the indices have been fully symmetrized. And the reason why I can assume this is that because you can show that every time that you have an anti-symmetric combination of matrices, this corresponds to something that you can write as Q of something with fermions. So anti-symmetric combinations of bosonic matrices are Q exact. And because we're looking at the cohomology, we want to throw away Q exact. That means that every combination of bosonic matrices that you have always implicitly been symmetrized. And then once they're symmetrized, you can use this identity and reduce the number of traces. So this, so we can apply this to this, and there's some expression with something, there's something of the form AB, 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 and I'm not going to write down the indices, minus or plus some coefficient times something like this. Okay? This is a trace relation that you can get to these matrices here, with coefficients and particular index structures. Okay, and that will do. So what are the effect of these trace relations on the number of, so trace relations have 3 effects. One, they reduce the single trace spectrum. Because if you try to, so this is a single trace operator. If you try to put too many of them, and every time you're going to put 3, you can always reduce it to a product of a double trace operator and a combination of double trace and triple trace. And we're also going to count multi-trace operators, and if you would count both independently, you would be double counted. So what this tells you is that the single trace spectrum gets truncated at small n, and in particular at n equals to 2, and you can never write something with more than 3 matrices. Okay, every time you reach 3, this combination is like a 2 by 2 matrix. This is a 2 by 2 matrix. This is a 2 by 2 matrix. You have 3 of them. Every time you have 3, you reduce. Okay, and so this reduces the single trace spectrum. It also reduces the multi-trace spectrum, and this is a bit more subtle. It reduces the multi-trace spectrum because there are particular cases. So if you take particular contractions of this, well, let me maybe try to write it down. If I take this and I put epsilon km, epsilon PQ is the last 2 B's, so Ln. I contract this particular contraction. I can show that this is equal to 4 pi I over k epsilon Rs, which I call Km, and then Q of, I'm not going to write down the indices, you don't care anyway, but something like this. So a particular combination of these things is equal to Q of something else. Okay? That's Q exact. That's what I told you before, that anti-symmetric combinations are Q exact. But I also told you that this thing, you can use the matrix identity to reduce it to, but this thing is also equal to AB, 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 minus AB, AB, AB. What does that mean? It means that because that a particular linear combinations of double trace and triple trace is Q exact. So we should not count this and this independently, because if we did, a particular linear combination is Q exact. Okay? So the net effect is you reduce the single trace spectrum, but you also reduce the multi-trace spectrum. And tracking this generically for arbitrary insertion of the letters at arbitrary end is extremely difficult. If you could do so, these are, I haven't told you this, but these are related to monotones. And this is why the problem is difficult, is tracking this would be a way to compute the finite end. If you could track this carefully, you could take the full superconformal index, subtract from it all the single traces and multi-traces, and multi-traces built out of these single traces, these BPS single traces, at finite n, and then you would, that would be taking z full minus z monotone. You would get the thing that counts only the fortuitous operators. And that is just very difficult to do in practice. So we can track these relations, we can track them at low order, but they become extremely difficult, and we don't know how to do it generically. Okay? So this thing together, if you do the full set of things minus these reductions, you get something which is like Zn monotones, which you can do at lower order, but it's hard to implement systematically. And finally, the third effect is that they add. So you might say, okay, maybe this gives us the full superconformal index. And you compare this thing to the full superconformal index, and you see, no, it misses some operator. And these are the fortuitous operators that it adds on top. Okay? And the fortuitous operators also are multi-trace, but they're not multi-trace made out of BPS single traces. They have some non-BPS components in them that happen to be BPS only because of trace relations. Okay, that's the general structure. Any questions? How am I doing with time? Do I have like, what, 10 minutes, 15?
More or less.
Yeah? 15? Great. So let me tell you about some results. Can I erase this? Yeah, now I can erase all of this. So, results. So one thing that you can do here that you cannot do in n equals to 4 super-Yang mills with gauge group SUN, because SU1 is trivial. But here you have UN, so U1 is non-trivial, so you can study the theory at n equals to 1. And that's already a non-trivial thing. So you study at n equals to 1. The cohomology problem becomes trivial in some sense. The specialty at q equals to 1 is that q psi equals 0. So it is true that you have that the cohomology problem becomes kind of trivial because of the fact that fermions anti-commute, and now you don't have matrices anymore. You have just C numbers for the field. So this is a bit special, but still the sort of monotone fortuitous story is not so simple. And you can start by doing the analysis at large K. That means no monopoles at all. Okay, you just use the fields in the Lagrangian. So you go to order X, the first order in the superconformal index, and you have these AI BJs, and like I told you, I and J can be 2, so you have 4 operators of this type. You go to order X squared, and then you have different types of operators. You have operators that look like this, and similarly with B. And I'm going to write 7 plus 1, and I'll tell you why in a second. These are the fermionic operators that have scaling dimension 1/2 and spin 1/2. But you also have multi-traces built out of these. And you have to be careful of using all the trace relations because I cannot put I, J, K, L arbitrary here. I don't get 2 to the 4 because some of them are the same. I'm putting traces here. These parentheses mean traces. But traces for 1 by 1 matrix is sort of trivial. I'm just putting them to tell you how you build gauge invariant blocks. Okay, so it's a bit of a cartoon. But because of that, many of these different things are actually the same because they're not matrices. You can just commute them through. So instead of having the full number here, there's only 9, which is not 4 times 4. Right? There's a reduction from 16 to 9 because many of these are actually the same. Okay? Good. And actually, the reason that I wrote 7 plus 1 is that already we have here our first example of a fortuitous operator. Out of these 8 possible, so you can pick I whatever you want, J whatever you want. But one particular linear combination of them, which is the antisymmetric contraction of I and J, you contract this with an epsilon tensor. That one is non-supersymmetric at n equals to 2. The only reason that it's supersymmetric here is that because Q just kills the fermions when you have C numbers and not matrices. But if you go to n equals to 2 or higher, then there's a non-trivial constraint that Q times psi needs to be 0, and that tells you that you can't make I and J antisymmetric. If you did, you would get something that is not Q closed. And so this is the first fortuitous operator that you can find. And to give you an idea, the first fortuitous operator in n equals to 4 super Yang-Mills happened at the 12th non-trivial order, much, much, much higher. And this is historically why when Chang and Yin tried to count the cohomology, I don't know, almost 20 years ago or 15 years ago, they said, there's no black hole microstates. At the time, people didn't know that the superconformal index had a complex saddle that grew like the Bekenstein-Hawking formula, and they tried to find explicitly the operators, and they said, look, we looked all the way to 11th power of x, we couldn't find a single one, so everything is a graviton. And they just didn't go to high enough order. Had they done that problem in ABJM 15 years ago, it would have completely changed the history, because they would have found it right away. Okay. Good. I think I will spare you small k here. That will be good enough for what I want to tell you about n equals to 1. Okay? So let me tell you about n equals to 2.
So this should be a representation of the commutant inside the SO6 of the supercharge, right?
Yes, this is the singlet. Thank you.
On SO4.
Yes, yes. So this one happens to be the singlet. These are currents. These sit in current multiplets. And there's an enhancement of the global symmetry at n equals to 1. And if you look at the commutant of the supercharge, in what so they always need to land in representation of that commutant, and this happens to be the singlet. There's there's 2 singlets. I think there's there's two and 2 bar representations, and then there's 2 singlets, and this is one of the 2 singlets.
So what's the symmetry at n equal to 1?
The global symmetry. Yeah, I forget, but there's an enhancement. There's a new global. I think it's in the extra U1. I think that appears at n equals to 1, and this is the fermionic partner in the multiplet of that extra current. Yeah.
I think usually it's just that the at least in other dimensions, the R charge can act separately on the bosons and the fermions. I think for when equal to 1. Maybe
could be. Yeah, could be. I forget the details actually. I would need to look into it exactly what the. But the global symmetry gets enhanced, and this is the fermionic. This guy is the fermionic partner of the enhanced R symmetry. Okay, good. N equals to 2. So now again, let's do large K. So no monopoles. And so you look at the first order. You have these ABs. Like I told you, there's 4 of them. You go to x squared, you have these A psi's. There's 7 of them. So this is why I'm calling this one fortuitous, is that you see one has now disappeared when you go to n equals to 2. So you have fewer BPS operators. So this one is extra at n equals to 1. It's fortuitous. And then you have the ABs. And like I said, there's a reduction here. Sorry, 16 was not the right count because they need to be symmetrized. But you have 10 here and only 9 here. So you see also some of the multi-traces disappearing like I advertised. Okay, then you go to x cubed. And now you can write many different things. There's the derivative acting on AB. There's things like ADB plus psi, some particular linear combination. There's AB cubed. There's AB squared. There's no 6 powers of AB inside because, like I told you, you can reduce things. And there's also psi AB, and psi A multi-trace AB. So these are all the things that you can write down, which are either derivatives or either you act with derivatives, or these are multi-traces built out of the building blocks that you had here. Okay. And And you count all of these together, and you compare to the superconformal index, and you realize that you're off by a factor of -4. What does that mean? You're missing 4 fermionic operators. Either you overcounted bosons, but we know we did the counting correctly, so we couldn't have overcounted bosons. Or it means that you're missing 4 fermionic operators. And these 4 fermionic operators are the fortuitous operators. Let me write them down. So what are these 4 operators? And we constructed them explicitly. They're the following. So ABJM. So that's the single trace term, plus there's a multi-trace term. And this is psi IA, J plus psi IB, J. Okay? And what happens is that, so there's 4 operators because, well, I and J are contracted, but K and L can either be 1 or 2, so there's 4 of these. And if you act on this with Q, this will transform the psi into ABA, or I guess in this case BAB and here ABA. It'll transform this into ABA. But then here you're going to have 6 A's, B's. So you can reduce that using the trace relation, and you reduce it in a way that exactly kills this. Okay? So Q acting on OF equals 0, but this is true only by using the trace relation that n equals to 2, and would be non-zero for any n greater. Okay, so these are the fortuitous operators. And you see that it's kind of interesting. They're built in a way by using precisely this extra thing, actually. So this extra 8th non-BPS, here there's only 7, which means that one combination is non-BPS. And that's exactly what appears here. So the way you make the operators, you use this sort of non-BPS single trace thing. You dress it with something that is BPS on its own. And you do some equivalent in the single trace term, and together they become BPS at n equals to 2. Okay? And okay, this might look like a complicated operator, but I dare you to go open the papers in n equals to 4, where it appears at x to the 12. I promise you it's much, 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 much more complicated than that. Okay, here this fits on 2 lines. It's a pretty simple operator. So that's one of the nice things about ABJM, is that you see these things appearing much nicer.
And essentially it comes because the structure of the operators is always AB, 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 and not like in n equals to 4 where we can have different powers, but
yeah.
the same.
The way I think about it is that in n equals to 4 super Yang-Mills, you cannot write trace x, right? Trace x is trivial because the grade group is SUN, right? Trace x doesn't exist, you have to do trace x squared. So the building blocks sort of start higher up, and I think that's why, whereas here you can, so x in n equals to 4, the equivalent in ABJM is not A, it's AB together, but trace AB exists. Whereas in n equals to 4, you sort of have to start here, and that's why, okay, now why it's x to the 12 and not 8, or like that's details I can't tell you, but that's sort of why it appears much further down, is that the matrices are traceless, whereas they're traceful here. I think that's the biggest distinction. Okay, so I'm done. I could tell you interesting things about small k. I want to take 2 more minutes just to explain to you what I think is a very interesting entropy puzzle that we realized by all of this. So let me just finish with that, and then I'll conclude. So what's the entropy puzzle? If you look at the Bekenstein-Hawking formula for these supersymmetric black holes in n equals to 4, what do you get? You get the following. Okay, so the Bekenstein-Hawking entropy goes like n to the 3/2. This is the famous n to the 3/2 puzzle of ABJM theory. There's a square root of k, and then there's some function, the order 1 function, that as long as delta is of order n to the 3/2 is some order 1 number. Okay. This is usually, this is the microcanonical thing at fixed energy. If you transform it as a function of temperature, there's this scaling, and then there's some function of temperature with temperatures of order 1. Okay. In the type 2a limit, so this is M theory, there's the same formula essentially, but you have to now use not k but n and lambda, and here you get n squared divided by square root of lambda, and again some order 1 function. And here now delta needs to be of order n squared. Okay, so what is the puzzle? The entropy puzzle is the following. This entropy, if you look at its k dependence, this entropy actually decreases as you decrease k. Okay, so the entropy goes down as k goes down. Okay? And this is very surprising because from what I told you, the way, well, I didn't really explain to you the monopole part when I did the results, what happens at small k. But I did tell you that when you have monopoles, there's more way to make gauge-invariant operators. Okay? So, so why is this surprising? It's surprising because if k is very small, then there's plenty of monopole operators that you can make. So there's many more ways to make monopole operator, to make gauge-invariant operators at small k than at large k. That means that if we were just counting all operators without -1 to the f inserted, this k behavior is not possible. It has to go the other way. It should be maybe divided by square root of k. It should increase as k decreases, because there's more way to make gauge-invariant operators. Okay, if you want the superconformal index, you can write it a sum over monopole sectors, okay, that are labeled by some charge q, and then each monopole sector starts as x to the k q over 2. So the smaller k is, the more monopole sectors contribute to a fixed power of x. Okay, and then there's like 1 plus, well, I mean it's not even 1, but then there's this is just a leading term, and then there's some interesting power expansion in x. Okay. So the way you can make gauge-invariant operators is enhanced at small k, not decreased like the entropy. And so this is so the only way this is compatible with the superconformal index is if there's crazy cancellations between the different monopole sectors. Actually, if you look only at the zero monopole sector and you compute the entropy, it's much larger than this. It goes like m squared times some order 1 number. Okay, so as you add in the different monopole sectors, the entropy gets reduced, even though there's more local operators.
So just what these formulas are at large n, right?
This is valid at large n. Yeah, this is the asymptotics at large n, and then delta scaling in this way.
And this reasoning that it would tell you that
this is also true at large n. I mean, of course, it becomes insanely complicated to track it, but no matter what n is, what I'm telling you here is true. There's just always more ways to do it. Okay, so. Yeah.
And the operators you showed us before that were like the actual formulas of trace something that you wrote before were at very large k. Do they change as you
Yes, but that's the point, is that if you go to small k, imagine n is, I don't know, 10,000 or whatever, and k is 10,000, or sorry, k is 10, then I can make so many new operators at k equals to 10 compared to k equals to infinity, because there's all the trace A, and
I just mean if I neglect the monopole operators, the ones that you actually wrote on the board, they still apply at finite k?
Yeah, these still exist at finite k. But if you count just those, you will get something bigger than this. And this is the puzzle. So what I think I'm telling you here is a new way to think about the n to the 3/2 puzzle that people have been confused about in a long time, and they made sense out of it in terms of saddles and localization and the associated matrix models. But this is like a reformulation of that puzzle in terms of actual counting of the states. And so, well, we don't know what the full solution is, but what we think happens is that actually, so it's true that you have many more ways to write operators. And in fact, if you look at the monotones, you see more monotones at small k. And that's because you have, supergravity on ADS4 cross S7 mod zk. The smaller k is, the less quotient you take of the sphere, and the more kk modes you have. So for the monotones, it works exactly in the way that I'm telling you. You have more possibilities, you get more states. Somehow for the black holes, the situation is reversed. And while I can't tell you exactly where it comes from, what we think is happening is that you have many more operators that you can write down, but actually you have even more new trace relations. So what we think happens is that as you decrease k, many of the operators disappear. And they disappear because now there's more operators that you can write down, but that means in principle many more trace relations. And what we think happens is that the trace relations dominate. And in particular, well, now I erased it, but this operator that I wrote down that appears at x cubed, if you look at the theory at n equals to 2 and k equals to 1, it's gone. It's no longer there. The fortuitous operator is gone. And it's gone because it has actually become a multi-trace component of lower dimensional operators that you already counted. So what we think the picture is, and we think this explains both the square root of k and eventually, if you could do it correctly, the n to the 3/2, we think that this behavior is really tied, so there's more operators, but there's many more trace relations.
And it's also possible that a small k you will have recombination of BPS short multiplets between monopoles and regular operators. That's another way by the number of BPS states.
Yeah, so good.
Yes, you decrease k.
Absolutely. So if you want to think about it in the usual way, you would say, well, small k is larger coupling. Things that were BPS can recompose and live together, right? That's what you're saying. Yeah. So I think a form of that is true. The part that's not so clear is why, when you do the cohomology problem, where you just count things, it really just looks like you have more possibilities.
We have to count monopoles and.
Of course you don't. You're doing a one loop thing. You don't really know how they combine and lift. So it's possible that what you're saying happens, but it's very hard to track it in that language. So I think that's the right intuition. We should remember that this is going to strong coupling. As you go to strong coupling, more things can lift. That's one way to think about it. But it's also true, and it's just explicitly true, that there's more operators to consider in the first place. And for the gravitons, this is the dominant effect. Okay, so more possibilities actually means more states in the superconformal index. And somehow, once you reach in the black hole regime, then the trace relations take over drastically and actually reduce, and we think that explains this factor here. Okay, and like I told you, we have an example at n equals to 1 and an example at n equals to 2, but we would like to have a more general story. Okay, I'm sorry for going over time. I don't know by how much, but let me thank you for your attention and stop here.
Okay, there has been already discussions, so let's go for the coffee break because we go 11:30.